Alright, so this next topic that we're going to talk about is called electron configuration. And you definitely want to focus here because this topic is actually kind of really important, but also really confusing if you're not following along. So what exactly is electron configuration? Just to put it in the simplest terms, it's describing the shape of the element based off of like what's on the outside. Now, if you remember, we talked about a couple slides ago, what is on the outside of the element? It's the electron clouds. The electrons are spinning around so fast on the outside of the element that they form like this cloud, and that cloud can have several shapes. Now think about this idea that shape is equal to function. For instance, if you wanted to eat a bowl of soup or some cereal, you wouldn't use a fork, you would use a spoon, and you can take a look at the objects, just look at their shape and realize what their function is, right? So same thing in this example with the electrons. If I have a specific shape for an element, that will dictate how that element is going to react. And it might react well with another element, it might react very poorly, or it might not react at all. And that's all based off of how many electrons it has and what those electrons are doing, what kind of shape they're forming. So that's basically electron configuration, but we're going to get into more depth. To start us off here, we got to understand that electrons move really fast. They're moving in like the speed of light fast, around 300 million meters per second. That's really fast. If I were to take an electron and put it on the equator and kind of shot it around the equator and spin around the Earth, it would move around the Earth approximately 7.5 times all along the equator in 1 second. So that's how fast electrons are moving. All right. Next point here, though, is that even though they are technically particles, electrons are so small that they also have like this wave-like characteristics. They also behave like waves. So they have what's called this like particle-wave duality. Even though they are particles, they also behave like waves. And you can kind of see in this picture on the left here that I kind of drew this out. This circle here represents like the spherical shape of the cloud, but the electron is actually traveling along this red path. And there might be two electrons here because you see two waves. And they kind of form like this wave form like that. And so this GIF here on the side, you have the nucleus in the center and the electrons moving really fast. They're dramatically slowed down in this case, but even they're just kind of showing you that they are moving fast. They form this cloud shape, but they also have like these waves that they're forming. So they're kind of forming like if you've ever seen like a slow-mo of like a guitar string being plucked or like a musical wave playing, they kind of look like that. And so we're going to go with that music analogy, and I'm going to kind of describe it with sound. For those of you that are musically inclined and play an instrument, this is going to make a lot of sense to you, I think. If not, I'm going to try my best to make it work for everyone, but we're going to go ahead and kind of compare this to music. So here's my music analogy. We know that musical notes make waves. You can actually measure the shape of that wave with a tool called an oscilloscope. You don't really need to know what that is, but you can measure the shape of the wave. And waves of different notes look different. So over here on the slide, I've got a picture of a C, and I'm going to play it on a keyboard here. That's what C sounds like. And then I also have the note G, which sounds like this. All right. And so those are called like natural harmonics, and these natural harmonics do exist with electrons as well. And so these are waves that will complement one another when they play them together, and they do sound good when you play them together with music. With electrons, it means that they behave well. Okay. So that also means that the electrons can make specific shapes with those harmonics. So if I have a C and a G at the same time, that's creating this picture down here where you have like both waves being played simultaneously. So remember, each electron is making its own wave. So when you have an atom that has like 90 or 100 electrons and they're all making that wave, they're making a very distinct shape. Going back to our previous slide here, take a look. Just this circular shape of this atom only has 2 electrons spinning around it. So it can get really complex, like what does the outside of the atom look like? And that's where we're kind of getting into the idea of quantum mechanics in electron configuration. All right? So let's take a look at the first orbital. This is called like the s orbital, and this is when you have a maximum of, let's say, 2 electrons. It's got a maximum of 2 electrons spinning around in a sphere. The S stands for sharp, but I like to remember it as sphere. That kind of helps me remember what does the s orbital look like. All right, and to kind of give you an idea of what that looks like, it's spinning in 3 dimensions. So if I cross the 3 dimensions, in the very center of this, there's the nucleus, and there's multiple levels, right? So with music, you can actually have multiple levels as well, right? So kind of making that music analogy with the first orbital, we've got a lower energy. Maybe that's something like a really low octave. Like if I play 2 electrons on a really low octave like that, and then on a higher energy level, maybe that's a higher octave. And then you can have a higher one like this, a third energy, like that. Now, what's to say that you can't have all 3 together? Well, you certainly could. You could have all 3 energy levels stacking on top of one another, just like how you can play multiple notes at once. So this s orbital looks like a sphere, and it's going to have electrons spinning around in that sphere, and each orbital for the s orbital can contain 2 electrons. Suppose I had 6 electrons. Well, I could fit 2 in the little sphere, 2 more in the big sphere, the middle one, and then the largest sphere, I could fit 2 more. And so I would have electrons spinning in all 3 clouds. And that's the final shape. I can see the outside. All right? The p orbital is called the principal orbital. And instead of the electrons spinning around in a circle, they're kind of forming waves, and they're forming this figure 8 going up and down. Okay? So if this is my nucleus. Imagine this is the electrons spinning up and down all around. But remember, this is only in one plane, so you can have it spinning up and down like this, side to side, and then like towards the screen and away from the screen, okay? So you have 3-dimensional views of this p orbital. You have electrons spinning this way. You have electrons spinning up and down like this. So this is like left and right. This is up and down, but this is left and right in a different plane. So 3-dimensionally, you can have all 3 of these existing as well, all right? So when you have all 3 existing, you've got electrons spinning in these clouds, and this is the final form, like what the clouds look like at the final form once you fill all of the p orbitals. You can have even more complex orbitals like this d orbital, which stands for diffuse, and this is where the electrons are not only spinning in the figure 8, but they're also kind of spinning around in like this loop around the center. So this is a d orbital. There's actually a lot of different shapes for the d orbitals, and it gets very complex. I'm definitely not expecting anyone to memorize all of these, but you can kind of see that it forms figure 8 in both ways for the majority of these, like these 4, the ones in the corners. They're forming like a figure 8, but then also another figure 8. So they actually form like this clover leaf pattern. And then the one in the middle is like a figure 8 with a donut around it. All right, so it can get really complex. Again, all 5 of these can exist simultaneously with electrons spinning around it. It can get very confusing with the shape. And then finally, there's the fundamental orbitals. These orbitals are really intense, and this is kind of reserved for the much larger atoms, probably like the biggest ones on the periodic table, the fundamental orbitals. We're not going to talk too much about these. We're mostly going to be looking at like s and p orbitals, and sometimes d orbitals as well. All right, so why does all of this matter? The reason, again, for this is because the electron shells help determine the element behavior, or how does it react, what does it react with, okay? So, for instance, let's say I've got 2 hydrogen atoms, and hydrogen's got 1 electron, okay? So, let's say I have just 1 electron, and it's playing 1 note, like that. And then this is oxygen, which has 6. So, I'm going to do my best to play 6 notes here. And then you add that 1, and then it kind of creates like this harmony amongst them. So that's when you have a really good chemical reaction, when it kind of forms this harmony and the electrons are spinning around each other very well. This is, again, getting into the realm of quantum mechanics. Really not going to talk too much about this. But there is a harmonic that exists between the electrons here. There can also be instances where a reaction occurs between 2 compounds, but they're kind of resonating at different frequencies and they're not really meshing too well. They can still work, but it may not work that well, so that bond could be easily broken. An example for that in music is, let's say you play like an F chord, or just like a part of an F chord, so like that, and then you also have like a G chord, so you have G and then F, and then you play them together. There's a little bit of dissonance, but it still works. But that's just an example of like how a chemical reaction could happen, but you could still break it apart because it's not really solidified in a perfect harmonic. It's just an example, going with the music analogy again. All right, so a good way to remember these shapes is that the S I like to think that it stands for sphere. I know it doesn't stand for sphere, but that's the way I remember the shape. S is sphere. P is for pole, like you have a north pole and a south pole. So you have two ends here. D would stand for dipole, where di stands for two, so two sets of poles. So kind of like a double version of the p orbital. And then F, I don't really have a word for that, but basically it's just a funny shape. So maybe funny. Okay, so S, sphere, P is pole, D is dipole. That's how I remember the shapes of the electron clouds. Are there limits to how many electrons you can put in each sphere? Yes, there are. So for each orbital or each lobe of the orbital, you can hold a maximum of 2. But an S orbital can hold 2. A P orbital can hold 6 because you can actually hold one here, and then there's 3 different versions of it. So if you remember going back to this slide here, so you can actually hold one electron here, one here, one here, one here, one here, and one here. And if you combine all of that together, you get 6 electrons. So the maximum of electrons you can hold on a p orbital is 6. For the d orbital, you can hold one here and one here. They're kind of forming their own figure eights. So 2 per each. 2, 4, 6, 8, 10. So a maximum of 10 electrons here. And for the fundamental, 2 per each. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14. So a maximum of 14 electrons for each f orbital. Okay? Now, how does that stack up? So what if you have like a lot of electrons? Like if you have a really, really big atom and you want to figure out what is the shape? Do you start with filling up all the s orbitals and then move on to p orbitals and then filling up the d orbitals and so on and so forth? Yes and no, kind of. You fill each orbital from lowest energy to highest energy. You do start with the spheres, but then you go down from the lowest energy, which is the first S sphere. And this does not necessarily mean that all of the S's are going to get filled up before all of the p orbitals, or that all of the d orbitals are going to get filled up before all the f orbitals. So there is an order to it, and I'm going to actually explain it with a good analogy right now. Alright, so here's how we would go about figuring out the order of the electron orbitals from lowest energy to highest energy. I've got this little sketch here, and pardon the lack of details here, but pretend this is a hotel, okay? And this is the lobby down here. I'm going to label it lobby. This black area right here, these are unavailable rooms, okay? So maybe they're under construction or maybe they're haunted, who knows? But those rooms are unavailable, okay? And there's 4 different size rooms for the hotel. And you might think, oh yeah, I would like to get one of the larger rooms, the d orbital or the f orbital rooms, because they're larger. But here's the caveat: they actually have more beds, so you have to share those rooms with a lot more people. Now, how many people? Well, the s rooms can fit 2 people. The p orbitals can fit, or the p rooms can fit 6. The d's can fit 10, and then the f's can fit 14. Okay, so that's how many beds you have in each room, and that's how many you can fit. So this is maybe like a budget hotel. That's our scenario right now. And then you have a charter bus with a soccer team. Maybe they're traveling somewhere and they're going to a different state, and they need to stop for the night somewhere to let their players rest and make sure they're ready for the next game. And they look for all the hotels, but this is the only one that's available. And so the coach talks to the main guy in the lobby and says, hey, we need rooms for 22 people. And the guy says, no problem, we got lots of rooms available. But the coach says, well, hold on. I noticed you guys don't have an elevator. You only have a set of stairs that go all the way to the 8th floor. That's really going to tire out all of my players, and I don't want them to be in worse condition for the game tomorrow, so I need them to get a lot of rest. So this is what I want you to do. I want you to fill up the rooms going from the bottom floor and up, and thinking about what's the easiest room to get to. Okay, so that's the scenario so far. And in this case, in this particular example, we're going to have 22 players on the bus. There's 22 players, and they have to fill up the rooms going from what's closest to the lobby and just kind of going from lowest energy in terms of effort getting into the room up to the highest. Okay, so that's the scenario so far. All right, so let's go ahead and start filling up those rooms. And I'm going to basically take one of these players one at a time and fill them up into the rooms. And it might make sense, obviously, that on the first floor, we're going to fill up that S room. So that's going to be 2 of those players are going to go into the S room because I can fit 2 players per S room. Okay, and that's going to be the easiest effort to get to that room straight from the lobby. No climbing stairs necessary, just first floor S room. The next easiest room is going to be after you climb the set of stairs. It's probably going to be this room up here. So it's going to be the 2S up here. I'm going to take 2 more players and fit them in there. Okay. The next room you might want to kind of think about. Okay, is it going to be this 3S room or is it going to be 2P? So what's easier? Is it easier to walk up another set of stairs, or is it easier just to walk down the hall a little bit? In this case, it's actually a little bit easier to walk down the hall. So we're going to take 6 players and we are going to move them into the P room over here. 6 of them can fit in here, just don't forget that. Going forward, the next easiest room to get into is probably the 3S room here. So I'm going to take 2 more players, move them in here. Okay. After that, you want to consider the same thought that you had before. Is it easier to walk down the hall into the 3P room, or is it easier to climb the set of stairs and go into the 4S room? Again, just like before, it's actually easier to go into the 3P room than it is to the 4S room. Okay? In fact, it's so hard to get up to the 4th floor here with all the set of stairs. Remember, if you have to stay on the 4th floor, you have to climb 3 full set of stairs. For some of you walking around in the school, you know that's not necessarily easy. You sometimes get winded going from the 1st floor to the 3rd floor. So adding another floor on top of that, the 4th floor, can be pretty exhausting. So what does that mean in terms of the 4 remaining players? Well, 2 of them feel up for the challenge. They're going to go up to the 4S floor, but actually going up to the 4th floor and down to the P room can actually be kind of hard. So they're going to say, forget about it. I'm just going to go to the 3rd floor and walk down the hall. So it's easier to get into the 3D room than it is to the 4P room. Okay, so there is kind of like this weird order of how you would go about filling up these electrons. It actually corresponds to this electron configuration potential energy graph that you have in your notes. I'm going to go ahead and come back here really quick. There we go. And so when we take a look at this graph, you can see that over here, right there, the S orbitals that we start at the bottom, that's going to be the lowest energy. That's the least amount of effort to get those electrons into there. So if we compare those soccer players to be the electrons, and we want to make sure that they're filling up the energy levels from lowest energy to highest energy, we're going to start with the 1S. And then we get to 2S, and then 2P, 3S, 3P, and then after this you kind of have to figure out what's lower. Is 4S lower than 3D? Just barely. So then you have 4S, 3D, and then the next one up is actually 4P. All right, then you have 5S, 4D, 5P, so on and so forth. So there's like this weird order of how you would fill up these orbitals one at a time. Now, what do these boxes mean? Each box represents like the number of beds. So each box can have 2 electrons. And if we compare that to the analogy with the hotel, each room could fit 2 beds. So like I guess one of those boxes can fill 2 of the players. There's 2 beds in there, for one for each player. So the S room can fill 2 orbitals. The P can fit 2, 4, 6. The D orbitals can fit 2, 4, 6, 8, 10. And then the F orbitals 14. Okay? So what's the order? This is the order of the electron configuration in which you would want to fill it out. 1S, 2S, 2P, 3S, so on and so forth. I'd like for you to take a moment and just write this down somewhere in your notes. I'm going to go ahead and hide here. And somewhere in your notes, write this order out all the way to 7P. It does go further, but we're not going to go past 7P. So just go ahead and write this down somewhere, and we'll come back. Alright, so hopefully you were able to get that down, and we are going to move forward and talk about how does this apply to individual elements. Forget the soccer player analogy, forget the music analogy we talked about. How does this apply to elements now? So let's actually use one of the elements as an example. We're going to start off with one of the lower elements, which is boron. And boron is a pretty small element. It only has 5 electrons. It has 5 protons and 5 electrons. So because it has 5 electrons, we're going to fill those electrons up going from the lowest energy to the highest energy. The lowest energy is going to be the first floor S orbital. So the S is going to be the lowest energy, and the first energy level is going to be the lowest energy level. So what I'm going to do is I'm going to put 2 of those 5 electrons right here. So I'm going to write it as like this superscript up here, this exponent. 1s and then 2. The 2 represents 2 of those 5 electrons. So then I have 3 electrons left, and I have to keep on filling them up into the rows. So 2s, 2. I'm going to put 2 more here, and then finally I have 1 electron left. I'm going to put it here. If I did do the soccer analogy, the way that would look is that I would have to take these 2 players and put them in the lowest energy level right here. So that's 1s, and then the number of players is 2. The next room would be 2s, and how many players go in there? Well, there's 2. And then finally 2p would be the next room, and even though I can put 6 players in there, I only have 1 player left, so he gets this whole room to himself. So I would write 2p1, so that would indicate that there's 1 electron, even though I could put in a maximum of 6. And so to check if that works, what you would do is add up all of the exponents here, the upper indexes, and the sum of the upper indexes, the small numbers, has to equal to the number of electrons. So in this case, I have 2 plus 2 plus 1, and that does equal 5, and that will tell me what element I'm working with. So in this case, boron, because it has 5 electrons, 2 plus 2 plus 1, that would be its electron configuration. Okay? What do the big numbers mean? Well, the big numbers only mean what level it is in. So boron sits in the second energy the second energy level, because that's the biggest number, the biggest big number. Okay? So the big numbers here, we have a 1, we have a 2, and we have a 2. The biggest of those is going to be this 2 shared over here. So that means it has the biggest energy level at level 2. If we compare to a different element, let's say we have sodium. Sodium has 11 electrons, and I can see that by counting all of these upper indexes. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 1 is going to be 11. Okay, so 2 plus 2 plus 6 plus 1, 11. That tells me 11 electrons, which means 11 protons, which means sodium. So that's actually how a lot of the periodic table was structured. What's funny enough is that all of these elements that are color-coded by what their shape is. So you can see that it's not just like a huge mix of different shapes. There is structure and order and regions of like what these atoms look like. These first 2 rows over here, they're all going to look like spheres because they all have s orbitals on the outside. All of the ones in the orange here, they're going to have d orbitals on the outside. All of these green ones have p orbitals, and the ones over here on the bottom, a lot of these are radioactive elements, have those crazy f orbitals. Okay, and then the energy levels, you can see here that this is the first row, so both of these have level 1. This is the second row, so this is level 2. This is level 3, 4, 5, 6, 7, and so on and so forth. Okay, so it goes up to level 7. And we have the different shapes corresponding to the different regions. What about elements with lots of electrons? For instance, let's say we go with like one of these bigger ones. I would say anything more than like 20 or so, you have a lot of electrons at that point. And so do you write out that entire electron configuration? Let's take, for instance, we have the element zinc, and zinc on the periodic table is right there. And so it's got 30 electrons. It's number 30 on the periodic table. So it's got 30 electrons. Would I want to write out that entire electron configuration? Let's check it out. 2 plus 2, 4 plus 6, 10 plus 2, that's 12. Plus 6 is 18, plus another 2, that's 20. Plus 10, that's 30. All right, and just making sure that the s orbitals and the p orbitals don't exceed their maximums. S can hold 2, p can hold 6, and d can hold 10. And it looks like they're hitting their maximums here. So we're good with that. But is there a way to abbreviate that? Is there a way to make that shorthand? And the answer to that is yes, there is a way to make that shorthand. And the way you do that is you have to find the element on the periodic table. So if I'm taking a look at this and I find zinc right there, I'm actually going to go up a row and then all the way to the right. Okay, so I'm going to go up a row and all the way to the right. And I am going to write the symbol of that element that I landed on. So up and all the way to the right, and then write down that symbol. And so that symbol is AR for argon. Okay? And so I write down AR, which, so in the example right here, that's where I write it, and I put brackets around it. Okay, so I put brackets around AR, and then I have to fill out the rest of the electron configuration. So what I did is I substituted the first few electrons with the symbol. How many electrons did I substitute? I substituted whatever number this gas is, this noble gas, or this element. So Ar for argon, its number is 18, so it's actually substituting for the first 18 electrons. Zinc has 30, I can substitute 18 of them just by writing the symbol, and then I have to fill out the rest. So, taking a look at this, I can substitute the first 18 with the symbol argon. So let's count 18. We have 2, 4, 10, 12, 18. That means I can take all of this and just cross it out, or not cross it out, not even write it down, but substitute it for argon. So I can take all of that and substitute it for Ar, just like that. Whatever's left over is what I have to write down after my symbol. So I substituted all of this for Ar. Maybe I should have made this yellow. Let me go ahead and make that yellow right now. And the remainder has to be written down after that. So argon, which is 18, plus 2, that's 20, plus another 10, that's 30. 30 electrons, that identifies the element zinc. Before we move on to the next topic, I'd like to work on practice problem number 5 with you. I feel like it might be a little bit too confusing to get through electronic configuration on your own at first. So what we're going to do is probably do like the first 5 or so, and then I feel like you can do the rest on your own. Okay, so taking a look at the first example, we've got bromine. If you have a periodic table handy, you can just look it up. If you don't have a periodic table, you'll definitely need one for this. But you could just look one up on Google. If you just type in periodic table, there's lots of images, and I think Google even provides you one. But if I try to find for bromine, I'm taking a look at my periodic table here. The symbol for bromine is Br. So I'm going to go ahead and type in Br, make this a little bit smaller. So be sure to also keep in mind which letter is capitalized and which one is not. I'm going to go ahead and keep going. Br on the periodic table, if I try to find bromine, it is number 35 on the periodic table. So I'm going to go ahead and put that in here for the atomic number. It's got 35 protons. Therefore, it probably also has 35 electrons. Okay? So let's keep that in mind, the 35 electrons, and we now have to figure out what the electron configuration is. And I went ahead and just pasted up the order up here from the slide that we just looked at. And so we're going to go ahead and fill those in together. We have 1s, and then we're going to put in a maximum of 2, so keep that in mind. 1s2, then I have 2s, 2, 2p, and I'm going to go ahead and put in a maximum of, hold on here, 2p, there we go, 6. Then I have, the next one is 3s2, and 3p6. And I'm going to just pause here, and it's good to pause every now and then and just remember how many we have and how many we need to get to. So we have 2, 4, 10, 12, 18. So I have a little ways to go. Then I have 4s2. You could also count along the way. So now we're at 20. Next is 3d10. So now we're at 30. And then 4p. And then can I fit my last 5 in this last p orbital? And the answer is yes, I can, because the p orbital can hold 6. So I'm actually going to put the last 5 in there. And just double checking my work, I'm going to only count the small numbers: 2, 4, 10, 12, 18, 20, 30, 35. Okay, so for bromine, that would be its electron configuration. The column over here that says the highest energy level, if you remember earlier, the highest energy level is the biggest big number in front. So we've got 1, 2, 2, 3, 3, 4, 3, and 4. So the biggest out of those numbers is going to be 4. That's the highest energy level. Okay, so that's bromine. Carbon, the element symbol for carbon is C, and it is number 6 on the periodic table. Therefore, its atomic number is 6. It's got 6 protons and 6 electrons. This one's actually going to be pretty easy. I'm going to take those 6 electrons and start filling in those orbitals. So 1s, there go 2 electrons right there, and then 2s, 2 again, so there's 4, and then 2p, 2. Okay, I'm not going to put in 2p6 because I don't have the whole 6. I don't have all of the electrons to put in there. So I only have 2, 4, 6 electrons, and only 2 go in that last orbital. My highest energy level is going to be energy level 2, because that's the highest, the big number in front. All right, and then we have sodium, the third one. Sodium on the periodic table is Na. That's because of it's a Latin root. Sodium in Latin is called natrium. That's where the Na comes from. And then it is number 11 on the periodic table. So we're going to put an 11 there. And we're going to fill out its electron configuration. So 1s, 2, 2s, 2, 2p, 6. In this case, I did have to fill out all 6. So let me go fix this. 2p, 6. And now I have 10. I'm left with one more. So I have 3s, 1. Okay. And what's the highest energy level? The third energy level. Okay. This next one, all they give us is the symbol Ca. If you find it on the periodic table, is calcium, and calcium is number 20 on the periodic table. So I'm going to put 20 here, and I'm just going to write in the word calcium. And its electron configuration is 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 2, 4, 6, 18, and then we have 3 more, so it's going to be 4s, let me format this right, 4s, 2. So 2, 4, 10, 12, 18, 20, yep, that's calcium. Highest energy level is the 4th energy level. All right, and then helium, He, that's right up top on the periodic table, so that's helium. And that's number 2 on the periodic table. So this is a really easy one, 1s, 2, with the 1 being its highest energy level. Okay, let's just do one of these small ones on the bottom. Let's do like the very last one, okay, the one where we actually have to count the electron configuration. So for instance, I've got 2, 4, 10 total electrons. So on my periodic table, number 10 on the periodic table is going to be neon. So I'm going to put in a 10 for the atomic number. The symbol for neon is Ne. I'm going to go ahead and type that in, neon. And then the highest energy level is the big number, so that's 2. So that's how you would do that. You just count the small number, the higher indexes here, the exponents, and that's how you would count the total number of electrons, which gives you the atomic number. All right, go ahead and try to figure out the rest of these on your own. I'm not going to publish the answers, but if you want to compare answers with each other, if you have time, you can go ahead and do that right now.